Yes, same the guy. Today we are going to talk about molecular geometry in chemistry. Here is what we are going to discuss. We're going to talk about the definition of molecular geometry. We talk about the valence shell electron pair repulsion model. Then molecular geometry in details, where we have the general rules to molecular geometry. Then molecules in which the central atom has lone pairs of electrons. Then molecules in which the central atom has no lone pairs of electrons. Then talk about the molecules in which with more than one central atoms. Then talk about dipole moments. So it's not much, but it's very broad. Yes, please don't forget to subscribe, like the video, and share. Let's go. Yes, what is molecular geometry? Molecular geometry is a three-dimensional arrangement of atoms in a molecule. Three-dimensional arrangement of atoms in a molecule, that is molecular geometry. And the arrangement of these atoms in a molecule, they can affect the physical and chemical properties of a molecule. They can affect the physical and chemical properties of the molecule. For example, can affect the melting point, the boiling point, density of the molecule, and the type of reactions of these molecules. So depending on the arrangement of atoms in a molecule, they can affect all these. Now, let's talk about the valence shell electron pair repulsion. The approach of studying molecular geometry, studying molecular geometry is known as the valence shell electron pair repulsion model. Why is it called valence shell electron pair repulsion model? Remember, in the outermost shell, we have the valence electrons. And those electrons are the ones which participate in bonding. And these electrons, they repel themselves because they have the same charges. So they tend to repel themselves maximally, such that the molecule can gain the stable arrangement or the stable structure where the repulsion is minimum. So we are going to see all that here in molecular geometry in broad. So the electrons, they repel themselves maximally such that they reduce the repulsion. Let's talk about the molecular geometry in details. The general rules of molecular geometry. General rules. Here, as long as the electron pair repulsion is concerned, double bonds, triple bonds, they are all treated as single bonds. They are treated as single bonds. We are going to see. Then, if an atom has more than one structure or resonance structure, atom is more than one resonance structure, we can pick any of the structures for molecular geometry. Then, remember, we can use the structure, like the Lewis structure, but the formal charges, usually they are not shown. In our molecular geometry, as we are going to see. If you haven't watched a video about formal charges and Lewis structures, please check they are there at MK the guy. Now let's go to molecules in which the central atom has no lone pairs of electrons. Yes, MK the guy. For the central atom, when there is no lone pairs of electron. Let's use an example. One, for example, if a central atom is attached to two surrounding atoms, that's the one we are going to discuss first. For example, barium chloride. Barium chloride. What is its geometry? Like the molecular geometry of barium chloride. So it will be barium attached to two chlorine atoms. So we don't show the formal charges. This is the geometry. And this geometry is linear. It's called linear geometry. So these bond pairs of electrons, they tend to repel themselves maximally such that they reduce the repulsion because they repel themselves. So they will be at 180 degrees. This angle is 180 degrees. Another example, when the central atom is attached to three other atoms. An example, we have boron trifluoride. So this A just represents the central atom. These are the surrounding atoms. So boron trifluoride, you have boron with three fluoride atoms. But the structure is not like this because these bond pairs of electrons, they have to repel themselves maximally such that they attain minimum repulsion. So the structure will be like this with boron and fluoride atoms. So these bond pairs of electrons repel themselves maximally. So this one is at 120 degrees. All of the angles are at 120 degrees. So this structure is known as the trigonal planar. These atoms, they are all in the same plane. They are in the same plane. Now, let's go to if an atom is attached to four other atoms. An example here, we can have methane, for example, CH4. Carbon is attached to four other atoms, which are hydrogen atoms. So this structure, we shall expect this. Let me do it here. Up. CH3, CH4, I mean. Someone would expect this structure. This structure here. But remember, these atoms, they are not in the same plane. So they can't be like this at night. They can't be like this. So the structure will be we shall have carbon atom. Then we have hydrogen atom here. Okay, let's begin with this one. Hydrogen atom. Another hydrogen atom. Then we shall have this and this. Shall have that structure. So all these angles, okay, this shows that this bond is behind the plane. It's like behind the board, the other side. This one is at this side from the board towards you. Then this hydrogen is on the plane and this hydrogen is on the plane. So These angles, they are at 109.5 degrees. All these angles, they are at 109.5 degrees. So if you find it like this, so it's the same structure. All these angles, they are at 109.5. So this structure is known as the tetrahedral. Is tetrahedral. The angle is 109.5. Let's have, if an atom is attached to 5 other atoms. 5 other atoms. An example can have phosphorus pentachloride. So the central atom has no lone pairs of electrons as these ones. Now, for this one, we shall have our phosphorus with a chlorine, another chlorine down, then you have another chlorine, and this. We shall have this structure like this. So this one shows that it is towards you. This one, it's the other side of the board. Or for easy, let it be like this. So this one is the other side, then this one is coming towards you. This structure, these angles here, they are at 90 degrees here. These angles, they are at 120 degrees. So it's like this. It's like this. This first, these angles, these 3 chloride atoms. So they are at 120 degrees of them. They are at 120 degrees, these 3. Then we have this and this. They are like crossing in like this. So this one, this chloride is at 90 degrees with this one, and this chloride is at 90 degrees with this one, and even this one. Because for these ones, they are on the same plane. Then this one is just coming like on the y-axis. For them, they are on the x-axis. They are flat. Then this one is on the y-axis. So these ones, they make angles of 90 degrees with all these 3. But these 3, they are making an angle of 120 at each angle. They are at 120. So this structure is known as trigonal bipyramidal. Is trigonal bipyramidal. Another example, let's have when the central atom is attached to 5 other atoms. To 6, this one is 5, so 6 other atoms. We say this one is tetrahedral. Then when the central atom is attached to 6 other atoms, for example, we have sulfur hexafluoride. Sulfur hexafluoride, we have the structure. Sulfur, it's in the middle. Then we have fluoride, another flow line. This one shows that it is coming from the board towards you. Then we have another flow line. It's the other side of the board. So it's same thing here. This one is coming from the board towards you. Then this one goes the other side of the board. So that's the structure for if a central atom is attached to 6 other atoms. So these angles, they are all at 90 degrees. It's like this. These 4, they are like this. They are on the plane. They're on the same plane. And they are making 90 degrees. Like this one is 90. This one is also 90. And this one is 90. They are all at 90 degrees. Then we have these two, they are on the y-axis. They are crossing like this. So they are also making angles of 90 degrees with these atoms. So these ones, they're on the plane. Then these ones, they come perpendicular to that plane. So they are all at 90 degrees. This structure is known as octahedral. Yes, those are the main 5 structures where the central atom has no lone pairs of electrons. We have the linear, we have trigonoplanar, tetrahedral. This one is trigonobipyramidal and octahedral. Those are the main 5 structures. Let's go to molecules in which the central atom has lone pairs of electrons. Yes, same the guy. We are on the atoms in which the central atom has lone pairs of electrons. So central atom with lone pairs of electrons. So first, we have to know that lone pair, electron repulsion. Lone pair, electron repulsion is greater than lone pair bonding. It's lone pair bond pair electron repulsion. And this one is also greater than bonding pair, the bond pair, electron repulsion. So that's the principle. If lone pairs are present, they repel themselves, then the lone pair and bond pairs repel themselves. And these ones, they repel themselves more than these ones repel themselves, as we are going to see. Let's have some examples. One, we shall have an atom attached to the 2 other atoms, and this central atom is having 1 lone pair of electron. So let's have, for example, sulfur dioxide. This sulfur dioxide, we have a sulfur as a central atom attached to 2 oxygen atoms. And remember, sulfur is in group 6. It has 6 valence electrons, meaning that these 4 plus the lone pair of electrons. So it's like we use the same structures we used before for those atoms without lone pairs of electron. So it's like this is the central atom is having 1 oxygen atom, another oxygen atom, but these ones they are treated as single bonds. So it is A attached to B, attached to another B, and here we have lone pairs of electrons. It's like this. Remember, we said if there are 3 atoms, we shall get a trigonal planar. If these were not lone pairs, this structure will be trigonal planar. But now this is not a bond, they are just lone pairs of electrons. Now it changes the name. Let's see. So it is now bent. It is bent. So if it was trigonal planar, when these ones were not lone pairs of electrons, these angles will be at 120 degrees of them. But here, since the lone pair repels the bond pairs more than these ones repel themselves, this angle will be less than 120 degrees. It's no longer 120, but it's less than 120 degrees. That's one. Another example. If you have a central atom attached to 2 other atoms, and we have 2 lone pairs of electrons. An example, we have water. Water. Remember, in water we have oxygen attached to 2 hydrogen atoms, but oxygen is having 6 valence electrons. So, meaning that these 2 plus these 4. So, oxygen is having 2 lone pairs remaining, which are not participating in bonding. So, remember, they are in 3 dimensions. They are not on the same plane. So, we shall have, remember, we said an atom, if an atom is attached to 4 other atoms, we shall have this structure. We shall have this structure. We shall have that structure. But now, for instance, now these 2, if they are now lone pairs of electrons, we said if there are 4, if this is B, this one will be tetrahedral. If they are not lone pairs, as we have seen. But now, if they are lone pairs of electrons now, it has changed now. These ones, they repel themselves maximally, and they repel these bond pairs, then these bond pairs repel themselves. Before, if it was tetrahedral, angle would be 109.5. But here, it won't be 109.5 because these lone pairs are now increasing the repulsion. So, this angle will reduce. So, we shall have oxygen atom with hydrogen and hydrogen with 2 lone pairs of electrons. And this angle is now 104.5, around 104.5. It's no longer 109.5 because we have increased the repulsion of the lone pairs. So this angle reduces. It reduces. Let's have another example. Another example, which is example 3. If a central atom is attached to 3 other atoms with 1 lone pair on the central atom. An example is ammonia. This ammonia, nitrogen is attached to 3 hydrogen atoms. And remember, nitrogen has 5 valence electrons, meaning that you have lone pairs remaining because these 2, 3, 4, 5. So now take as this lone pair to be a bond. If an atom is attached to 4 other atoms, we expect the structure to be tetrahedral. Tetrahedral. But now, This is not a bond. It's not a bond, but they are lone pairs. So it will change. We shall have nitrogen with hydrogen, and another hydrogen. So this one is coming out of the plane, this one is the other side of the board, and this one is on the board. So that geometry means that this structure is different from tetrahedral, but as if it comes from tetrahedral. This structure is called trigonal pyramidal. Another example, if we have a central atom connected to 4 other atoms with one lone pair of electron on the central atom. For this one, we said if it was tetrahedral, angle is 109.5, but this one will be less than 109.5 degrees. Now here, we have a central atom and 4 other atoms attached. But we have a lone pair of electron. So this is B. So take this one as the lone pair of electron. If there was no lone pair of electron, it would be a trigonal bipyramidal. But now, one of the atom is a lone pair of electron. So this atom will change everything. This structure will change. It will be like this. We shall have the angle will reduce. So this is the lone pair. I put it here. Now this B, we shall have this B and another B. So these terminal bonds, or the terminal atoms, the angle reduces. It's less than 180 degrees, not like this one at 180. And these ones were at 120 degrees, these angles. But now they will reduce. They are less than 120 degrees. They reduce because of this lone pair of electrons. It's like this atom. So it's like this is the lone pair, this is the B. So this one reduce again, and these ones they also reduce because of the repulsion. This structure is known as the distorted tetrahedral. It's like tetrahedral but distorted, or sometimes called the seesaw, as you can see. For example, if you rotate this structure, you have this, as if it's like this, like a seesaw. I see. So that's why it's called sometimes seesaw model or seesaw structure or distorted tetrahedral. Let's have like 2 more examples, then we yes, I'm the guy. Let's have another example, which is example 5. So if we have a central atom attached to 3 other atoms with 2 lone pairs of electrons. So it's like we have our central atom. Now let's take as if these ones they are also bond electrons. So we shall have here B, another B, we have B and this lone pair, and this one as a lone pair. So if it's like this, when these ones they are like also atoms, this structure is trigonal by pyramidal. But now, since these are lone pairs of electrons, the repulsion increases. So we shall have A with B and B with lone pairs of electrons. This structure is called T shape. This is T shape. There's another structure, for example, if a central atom is connected to 5 other atoms with one lone pair of electron. So this one will be like this. We have B with B. So this one is as if it's a lone pair. We have B and this one is B. So if a lone pair behaves like a bond pair of electron, we shall have this structure which is octahedral. It's like octahedral. But if we change, remember this octahedra, all of them, they are at 90 degrees. If we change, okay, let this one be here for easy understanding. This one here. Now, the repulsion increases, meaning that this one, the lone pair, will increase the repulsion of these ones, meaning that the angle won't be 90 anymore. They won't be at 90 degrees. And we shall have a structure known as the square pyramidal. Another example, if you have a central atom with 4 other atoms attached, and this central atom is having 2 lone pairs of electrons. I think for this, you shall comment with the answer in the comment section. Let's go to molecules with more than 1 central atoms. Yes, I'm the guy. For molecules with more than 1 central atom, with more than 1 central atom. First example, let's have methane, which is CH2OH. This is methane. We have 2 central atoms. We have a carbon and oxygen. So we shall have this carbon is having 2 hydrogen atoms attached, and we have oxygen with hydrogen atom attached to it. So you have to consider both of them, but you consider one at a time. So for example, this carbon is a central atom. It's attached to 3 other atoms, and remember, carbon has no lone pairs of electrons. So these angles will be at 120 degrees of them. But oxygen in this structure is having 2 lone pairs of electrons. And remember, if you are to consider oxygen, its structure will change now. We shall have bent structure like this with lone pairs of electrons. So this angle will change. It's like that of water, which is 104 4.5 degrees. It won't be at 90. At 180 degrees, it changes to 104.5 like that of water, because oxygen is having two lone pairs of electrons. Let's have another example, which is example 2. For example, if you have ethene, which is C2H4. Remember, ethene, you have a double bond between two carbon atoms, and each carbon atom is attached to two hydrogen atoms. And we say that double bonds, they are treated as single bonds, either double or triple, they are treated as single bonds. And remember, each carbon atom has no lone pair of electrons, so they are all like the first structures we did. So each carbon is attached to, it's like to 3 other bonds. It's like this. The double bond is treated as a single bond. So though it's double bond, but they are treated as single bonds. These are hydrogen atoms. The hydrogen atoms. And since the carbon is attached to 3 other, it's like 3 other atoms, all the angles will be at 120 for all. They are all at 120 degrees. I think these examples, they are enough. Let's go to dipole moments. Dipole moments. What are dipole moments? Dipole moments, they are vector. They are vector quantities that measures the separation of positive and negative, of positive and negative charges of atoms within the molecule. So the vector quantity that measure the separation of positive and negative atoms within a molecule. So, for example, if we have hydrogen fluoride, this bond is a covalent bond. The electrons are not pulled, like they are not pulled completely from hydrogen atom. So means the electrons, they are shared, but since this fluorine is more electronegative, and this is less electronegative, the electrons will spend more time in the vicinity of hydrogen, of the fluoride atom. So we represent the dipole moments like this. An arrow, it's a crossed arrow. So this one will be the dipole moment. So we shall have this hydrogen and fluorine. This one will be represented by partial positive charge, because as if it's losing the electrons to the fluorine. And this one will be partially negative. So we shall have this. So we represent the dipole moments as it goes, the electronegativity goes to the fluorine atom. Another example, for example, carbon dioxide. Let's see whether it has dipole moment. Carbon is attached to two oxygen atoms, and this oxygen is more electronegative than carbon. The oxygen atoms, they are all electronegative than the carbon atom, meaning that this one will pull towards this side, and this one will pull towards this side. So we shall not have net dipole moment, meaning that this one has no dipole moment. because they cancel each other. They cancel themselves. Let's have other examples. For example, if you have ammonia, this is the structure. This is the structure of ammonia. Remember, nitrogen is more electronegative than hydrogen atom and shares lone pairs of electrons. So the dipole will be pulled towards nitrogen like this. And these hydrogens, they are also being pulled by nitrogen. The electrons are being pulled towards nitrogen. So the dipole we shall have a net dipole moment because nitrogen is pulling and these ones they are also being pulled. So we shall have a net dipole moment. So this one has dipole moment. Hence it is polar. Here also this one is polar, but these ones this carbon dioxide is non-polar because it has no net dipole moment. So it is non-polar. Let's have another example. For example, we have nitrogen trifluoride. In nitrogen trifluoride, we have this. Almost same structure like this. Remember, fluorine is more electronegative than nitrogen. But nitrogen shares also its electronegativity and shares one pairs of electrons. So it shall have its dipole goes like that. Then these ones, they are all pulling. They are all pulling away from nitrogen. So the net dipole will be 0. The net dipole is 0. Hence, this structure is non-polar. Ammonia, this is 3, not 4. Ammonia is polar, but nitrogen trifluoride is non-polar. Why? If you can see the dipole moments. If you have C2, H2, Cl2, we can have two structures from this. We can have this. It is 1,2-dichloroethene. It's 1,2-dichloroethene. We can have the cis form, but again we can have the trans form. So we want to check whether these two have dipole moments. Chlorine is more electronegative than carbon, so we shall have dipole moments goes like this. Even here it goes like this. Carbon is pulling from hydrogen, so there is also dipole moment towards carbon. Means that this structure will have a net dipole goes like this. So this one has dipole moments. When it comes to the transform, this chlorine is pulling towards this side, and this chlorine is pulling towards this side. This carbon is pulling towards itself, and this one is pulling towards itself. So I think the dipole moments they cancel themselves. Yeah, the dipole moments cancel themselves. Mean that this one has no dipole, moments. So the cis form has dipole moments, but this one has no dipole moments that transform. Yes, it's same kind of guy. Thanks for watching. Please don't forget to subscribe, like the videos, and share. Thanks so much.